All right, so now let's discuss molecular shapes. We can actually use Lewis structures and predict the shapes of molecules. Gives us lots of useful information. Um, Chemical and physical properties are both related to the shapes. We'll look at we use Lewis structures to show atoms and bonds, but we don't really get spatial arrangements, spatial orientations that the 3D look at what these atoms look like. Versus molecular models, we can actually show orientations, bond angles, helps us understand lots of chemical and physical properties, solubilities, reaction mechanisms, chirality, optical properties. So a lot of this in future chemistry and science comes from trying to understand what the shapes of molecules are. So we do this really from the Lewis structures. Again, just show some basic orientations. I think, well, first, before we get into that, look at a couple of examples. I actually want to cover this first. And there's some terminology here to have to be careful about. It can be a little bit tricky, but if you understand the concepts, it makes it a lot simpler. The first is what's called valence shell electron pair repulsion. And I think we're getting to that. I want to show you some examples of that. What it's really saying is that electrons repel each other. Sort of makes sense. If you look at bonds around various atoms, the bonds are actually composed of electrons, and electrons don't want to be near other electrons. Now, take something like there are some. I'll go through use a couple of examples that are really exceptions to the octet rule. There's beryllium chloride, I believe, is an example, which beryllium only wants actually 4 valence electrons around itself. It actually gets back to formal charges, and the electronegativities aren't strong enough to form a full ionic compound. So the basic, I'll draw it like this. This is Lewis structure of beryllium chloride. Look at formal charges. All formal charges are 0, so that's why this works out. I drew it this way to show you that, to remind you or stress that the way we draw Lewis structures on paper, in most cases or many cases, does not represent the way the molecules actually look. So I could have drawn this as a linear molecule, which is probably what you would do for the most part, but really just for an example to stress that this is a valid Lewis structure with bonds drawn like this. But I do this also to show you the point of this chapter, this section. Both these bonds consist of electrons, and the electrons surrounding the chlorine atoms also repel the electrons on the other chlorine atoms. They don't want to be near each other, and we've discussed already that atoms bond to become more stable. And the way these bonds form, they want to form the most stable configuration they can. And so the angle between these bonds, since these electron pairs repel each other, these groups of electrons repel each other, the angle should be as large as possible. That's going to minimize the repulsive effects. So to be more stable, as you would like to draw it anyway to begin with, probably, we have, of course, 180 degrees between these two atoms, between these two bonds. That gives us a linear geometry. So let's take another exception to the octet rule. Again, I don't expect you to know these exceptions, but they serve a good purpose for these examples. The boron only wants to have 6 valence electrons around it in many cases. So this is a Lewis structure for boron trihydride. Now, in this case, we want to maximize the angle of separation between these bonds. The bonds, again, are composed of electrons. The electrons repel each other, so we want to maximize all these angles. Of course, the angle on the bottom is 180, but the others are 90. That doesn't make sense, so we would expect them to be nice and symmetric. You might guess to make all these as symmetric as possible, take 360 divided by 3. Then these angles really should be 120 degrees, even though that's not the way it looks, the way it's drawn. So we would draw this more accurately like this. A very good trigonal structure. This is called a trigonal geometry because it's three bonds symmetrically around the central atom, and they're all 120 degrees. This also shows you why we don't often represent the true bond angles on paper because it's harder to do. Right angles are much easier on with most computer software. Fits into papers better, so that's what you quite often get. So let's look at one more case. Let's look at methane, ch4. So this is methane, and so we need to get these bond angles to be the maximum possible. So you might want to ask yourself, what do you think the maximum angle possible would be? Well, if you took 360 divided by 4, that would make sense. But the actual maximum angle for this between these carbon-hydrogen bonds is 109.5 degrees. I wonder, how can that be? Well, that adds up to more than 160, or more than 360. So the thing is, molecules don't have to stay in 2 dimensions. They're 3-dimensional space, and they can actually form a tetrahedral structure. And that's what this is. So this is a tetrahedral geometry. These are the 3 main geometries I want you to know for 104. For 105 and 6, you'll need to know some other ones, but it's a good basis to start with. At least the other ones I want you to memorize. You can look up, some of the other ones for some exercises in the text and on Blackboard. But as far as exams go, I want you to know these 3 basic ones now. You can expand on those later. And so let me show you this one because this is a little bit tougher to visualize. Okay, finally got this to work. Anyway, this is a methane molecule. Where since we can use 3 dimensions, you can see it's a tetrahedral geometry. If you've ever seen a 4-sided die, 4-sided figure, it's like a 3-sided pyramid. You got the bottom and then the 3 sides, where each corner is one of the hydrogen atoms. Nitrogen is in the very center of the pyramid. And so this is a tetrahedral geometry. Again, this allows the methane atom to get bond angles greater than 90 degrees. So 109.5 degrees is the angle, the maximum angle for this type of geometry. So I think it's easier to visualize it versus trying to draw on paper. We try to represent it on paper, but it's awkward sometimes. So that's what this is talking about, the VS-EPR theory. One thing I don't like about this theory I wanted to mention is the electron pair repulsion. I think this is a bit misleading because when you get, it's talking about basically the groups of electrons around an atom repel each other, which makes sense, but when you had double and triple bonds, the double bonds stay as a group, the triple bonds stay as a group. So electron pair can be misleading. Students try to split apart double and triple bonds. Just remember you can't do that. So I tend to think of this as electron group repulsion instead of pair repulsion. So a little bit of semantics, but I think it helps you visualize the concept a little bit better. And there are 2 different types of geometry. The text calls it electron pair geometry. I don't like that at all because, again, it's more electron group geometry. So this is electron or electronic geometry. I've seen both used quite a bit, so just want you to be familiar with both terms. Versus molecular geometry. So they're slightly different, and they're both very critical. You need one to understand the other. Electronic geometry is 3-dimensional arrangements of bonding of electron pairs, and again, I meant to change this in the slide. I really prefer electron groups. If it will cooperate. Doesn't like me changing their text, I guess. Electron groups and lone pairs of electrons around the atom. It's what we just did. An unshared pair of electrons has the same repulsive effect as a bond. Actually has more repulsive effect, but we can split apart. We use that to determine the basic geometry of our molecule, the basic electronic geometry. So electronic geometry really tells us the angles between groups of electrons, where the molecular geometry is looking at just what shape do the atoms themselves form. A little subtle difference, and we'll go through this and give you some examples so it'll make more sense later on. Now, the book basically talks about steric number. This is sort of the same thing. We're taking the number of atoms bonded to an atom and the number of lone pairs around a given atom to determine how many groups we have around that atom itself. The steric number is how the text refers to it. And use this to determine the maximum or the most stable spatial arrangement of these groups around the central atom. So, like we just did, if you have two groups, you would have a linear arrangement. You have three groups, like we looked at, you would have a trigonal arrangement. Four groups, more of a tetrahedral arrangement. So, let's first look at atoms with no lone pairs, like we just did in the examples. No lone pairs are really easy to see, so it's pretty straightforward. With just two atoms, you have linear geometry, like we did with the beryllium chloride. With three atoms bonded to the central atom, we get trigonal planar, or trigonal, it's often called. Planar is implied. There's also trigonal pyramidal, so be careful about that. Like with the boron trihydride. With four, like with methane, you get a tetrahedral. Then there's trigonal bipyramidals and octahedrals and lots of other. You can have a square planar, which is kind of weird, but it does happen sometimes, and a few other geometries. But for right now, I want you to really concentrate on the first three cases: linear, trigonal, and tetrahedral. And one more we'll have to mention in a bit. So as we said, these are the angles we just went through. That's what you might expect. The tetrahedral comes out a lot, and this is, again, the geometry we talked about with methane. And again, these are the lines between the atoms, sort of clarify. So you get a three-sided pyramid. I will mention, let's back up a second, the trigonal bipyramidal is basically taking two of these pyramids and putting one on top of the other. That's all. So you can visualize that. When you get to organic chemistry, you have organic models you can play with yourself. It makes a lot more sense. It really helps visualizing these different geometries. And these are just examples of molecules that have these different types of forms. So I'll go through that as an example in a bit. Now, the issue comes into play when we have lone pairs of electrons. What do we do with those guys? And that's what this is showing us. If we have, like SO2, for example, we have three groups of electrons. If you look at the Lewis structure over here, as resonance structures, we'll look at just one resonance structure. Around the sulfur, we have one group of electrons here, the single bond. We have this bond over here, another group of electrons, and we have this unshared pair of electrons. So there are three groups around this central atom. So it's a trigonal electronic geometry. Electronic geometry really tells us the angles between all the groups. So we know that the angles here are going to be roughly 120 degrees. Back there. Between any of these groups, since it's trigonal, it's going to be about 120 degrees. Now it ends up that since lone pairs actually have more repulsive effect than the bonded atoms, it kind of distorts this a bit. So the lone pair oxygen bond angles will be more like maybe 122 degrees or so. The oxygen-oxygen bond will be maybe 118 or so, a little bit less than 120, but still it's basically a trigonal structure. So again, over here is the electron geometry, or again, they call it electron pair geometry. I just don't really like that very much. But the molecular geometry, we look at just what shape does the molecule itself form? What shape do the atoms themselves form? So the atoms, again, even over here, I'll show it on this one, this resonance structure instead, just forms this geometry. This is the other geometry I mentioned you need to know. It's just called bent or angular. Not a very good G there. So it's bent or angular geometry, same thing. And really that means it's not linear. You can have another good case of angular geometry. Let's take water. Lewis structure. Is that. So simple enough. We have, in this case now, four groups of electrons. We have 1, 2, 3, 4 around our central atom. So the electronic geometry would be tetrahedral. And what this tells us is the angle between all these groups is going to be 109.5 degrees. And that's very critical because if we want to say what is the molecular shape, the molecular geometry, we only look at the atoms in this molecule. But even though this is drawn where it looks like it's a linear molecule, the molecular geometry is going to be bent. You know, it might be proper over here. I'll write let you see. If you want to actually represent the actual angles more accurately, we might draw the molecule something like this. But again, that's kind of awkward. So this is where it helps to visualize the molecule so that what you see on paper you should know is not necessarily what the molecule looks like. So this is the bent geometry. And this is, as we're saying, we have some fluctuations in bond angles. I'm not going to try to, I don't want you to worry in detail about these right now, but you should be aware that different bonds, different unshared pairs of electrons, single versus double bonds, all have different repulsive effects. So they can distort this a bit. For 104, really just want you to think of, again, the three main geometries, trigonal or linear, trigonal, tetrahedral, but be aware that lots of molecules are not exactly these geometries. Unless they're exactly symmetric, then you'll have some deviations from these angles. Lone pairs have more repulsive effect. Bonding pairs have less. Multiple bonds have more repulsive effect than single bonds. So triple more than double more than single. So it's pretty straightforward. And this is showing another example. This is like ammonia. We have 4 groups of electrons, so you basically have 109.5 degrees between the groups. But since the electrons up here have a little more repulsive effect, they push the hydrogen atoms away a bit more. So instead of these guys being 109.5 degrees between each other, the angle is a little bit less, but it's still basically a tetrahedral electronic geometry. And now you can see they changed their term to electronic group versus electronic pair. I think I like that a little bit better. But the molecular geometry is, well, in this case, what's called trigonal pyramidal. It looks almost like a tetrahedral shape, but it's kind of a squashed pyramid. That's just one more shape that comes out quite a bit. Again, we just went through that example, so another example you can look at. You have some odd things happening here, and you'll get to more of these other cases in 1 and 5 and 6.